get right into it. So today's lecture is about the relationship between physics and computing. It's a big subject, and actually I'll be spending 2 lectures on it. In this lecture, I'll mainly do the conceptual basis of computing, classical computing in physics, and give some important examples of it. And next time I'll talk about the technology of computing and the frontier of quantum information theory and quantum computing. So really, I think this subject is best approached through highlights and case studies. And I'm going to focus on 3 things in this lecture. One is the simulation of fundamental physics. Secondly, physical approaches to an important class of computing problems called optimization. And then the relationship between computation, erasure, and heat. This is part of the subject of the relationship between information and energy, which goes very deep and will be a theme we'll elaborate on both in this lecture and the next one. And as I said, I won't have to, I have decided after seeing how much material there is to move this last part, technology of classical computing, into the next lecture. So even though it's advertised as quantum computing, it will contain the technology of classical computing at the beginning. Okay, so our first subject is simulation of fundamental physics. And I want to highlight that with a part of fundamental physics where computing has had a tremendously profound effect, and it's really changed the way we do the theory. That's in the theory of quantum chromodynamics, QCD, our theory of the strong interaction. So I'll give a fairly deep case study of how that works. And then I'll say a few words about speculations that the laws of fundamental physics might be best formulated as rules for computing, as algorithms, as opposed to the way it's been done in the past as sets of equations. So let me start with something that might seem a little in left field for our main subject, but turns out to be quite central. That is the old notion of an ether. When James Clerk Maxwell in the mid-19th century tried to formulate the laws of electricity and magnetism and relate those phenomena possibly to the phenomena of light, he made a model of the behavior of electric and magnetic fields based on mechanical objects, based on kind of rotating gears and lubricating elements in between. I won't go into the details of this model, but it was a way of getting a substance that was made in terms of mechanical elements that behaved insofar as the way it supported flows of energy and momentum that behaved in the same way as electric and magnetic fields. When Maxwell did this, because his model was forced to satisfy the general principles of mechanics, like energy and momentum conservation, and it turns out conservation of electric charge was also built into this model. It captured so much of the electromagnetic, the reality of electromagnetic fields, that he was able to predict new phenomena and arrive at what we now call Maxwell's equations, which are the equations we still use to describe electricity and magnetism. But the lesson here is that electric and magnetic fields can be modeled in terms of other things that obey simple rules for how they move. Maxwell purified this to make the electric and magnetic fields more abstract in his later formulation. So he took away the underlying gears and flywheels and lubricating elements and just had fields in space, electric and magnetic fields. And however, you can sort of, if you squint, you can sort of see the underlying model still there. That electric field, the equations of Maxwell say that the electric fields flowing out of a certain surface reflect the charge inside, that changing magnetic fields generate electric fields that circulate around them, changing electric fields give circulating magnetic fields. I'm sorry, this is changing magnetic fields giving circulating electric fields, and dual effect, and so forth. So these were Maxwell's equations for his purified ether. So the original one was kind of a mechanical or computational model. The purified ether, which satisfies the same equations, was the model that we use today of electricity and magnetism. By the way, there's a myth going around that the ether doesn't exist. The ether actually does exist, and we'll say more about that as we go on. So quantum chromodynamics, our theory of the strong interaction, is heavily influenced by quantum electrodynamics. It uses equations of very much the same sort, but I like to say that quantum chromodynamics is like quantum electrodynamics, like electrodynamics on steroids. Instead of one electromagnetic field, we have 8 gluon fields, and instead of one kind of charge, electric charge, that can come in positive and negative forms, but it's just one numerical measure of charge. In QCD, we have 3 different charges, which are often called colors. In any case, it's a kind of Maxwell on steroids. And the reason, and according to the theory of QCD, what protons is not fundamental particles, but very complex assemblies of quarks. These balls here represent quarks, and there are 3 different kinds representing the 3 different colors of colored charge that you can have. And the gluons are these squiggly lines which interact with the quarks and get exchanged. These are like photons, but they come in several different, 8 different varieties, and can exchange, react to the colored charges, not electric charge. And experiments that take snapshots of inside protons, it turns out that by using a technique called deep inelastic scattering, you can take snapshots of what's going, after a lot of information processing, you essentially get snapshots of the inside of protons, revealed that they were complex objects, not fundamental particles, and had hard bits inside which carried charge. Those were interpreted as the quarks, and also other things that did not have electric charge but do carry energy, and those are the gluons. So experiments gave us snapshots that you could interpret in this way, and then the theory gave us equations that tell us about the elementary interactions in these between these objects. But the equations are very difficult to solve. And in fact, the closer you look at a proton, if you look at it with finer and finer resolution in space and time, it looks more and more complicated. You see more and more quark-anti-quark pairs that come into existence and weaken out of existence very rapidly. They don't travel very fast. So very far, I'm sorry. So if you don't have good resolution in space and time, you don't see them at all. But as you get better and better resolution in space and time, you find that the proton is really densely packed with gluons and other things. And the description in terms of distinct particles that build up to make a proton actually is very inconvenient. And the better description is in terms of fields, which contain many, many quarks and gluons, just as electromagnetic fields contain many, many photons. So according to the pictures, they suggested a theory that contained quarks and gluons as the basic degrees of freedom, the basic building blocks. And gave us we postulated a theory that in fact used those as the basic building blocks. But then there was a big problem with that, because in free space, as opposed to inside protons, you never see quarks or gluons. What you see is sometimes quarks and antiquarks bound together in objects called mesons, when you have a quark and an antiquark, plus possibly a lot of gluons and additional quark-antiquark pairs, or baryons, which are the things like protons and neutrons that have 3 basic quarks, plus a lot of quark-antiquark pairs and gluons, and other stuff, lots of other things that have slightly different body plans or are put together from mesons and baryons. But what you never find, are individual quarks or gluons. This is a very peculiar thing. It's as if you had, like the Cheshire Cat, where these the quarks and gluons have a kind of insubstantial existence. When you try to pin them down, they don't exist. They're always inside other things. So this was unprecedented in physics, and it became a question: can a Maxwell-like theory built from quarks and gluons instead of being based on electrons and photons, can that produce the world we observe? Maxwell's theory, extended to theory of electrons, describes atoms and atomic physics and chemistry, and does that in a way that builds up from quarks and photons, from electrons and photons, but you do see the electrons and photons, so it's not so mysterious. You build up from building blocks that you can separate and study individually. But in QCD, the behavior you needed was that the underlying basic components of things can't exist on their own. Was that something that was possible, or was it something that emerged? Is it something that emerges from the actual equations we relate to? Now let me show you a picture. So people had to try to solve these equations as best they could, and it turns out that in order to do a decent job of solving them, it was necessary to make a model of the equations, which were very much like Maxwell's ether model, with degrees of freedom that fill all space and move around, and use supercomputers to calculate the behavior. Now, these are quantum mechanical fields. They obey the rules of quantum mechanics, which means they fluctuate. So they're uncertain in their values. And that means even in what we perceive as empty space, there are short-lived fluctuations in energy and in the values of the fields that are going on all the time. And you can numerically, you can calculate that activity. And what this is then is a picture of empty space. The resolution of this picture is like 10 to the minus 14 centimeters in space, and the time resolution of the snapshots that go into making the film is about 10 to the minus 24 seconds if you scale from the computer simulation to the physical behavior that it's simulating. So if our eyes were much more nimble in what they could see and could see with much higher spatial resolution, this is what we'd see. But our eyes were evolved to ignore all this, and it takes a lot. It actually takes a lot of energy and sophistication to bring out this behavior in with ordinary receivers, but numerically we can see what's going on in empty space, and this is a picture of it. So what this is in detail is fluctuations in the energy of gluon fields that come to be and pass away. These are called virtual particles that are manifesting the kind of spontaneous activity that one has in quantum theory. I'm going to let the author of this, whoops. I'm hoping to let, oops. Here we go.
One of the most amazing things about atoms is
They
are mainly empty space. If an atom were as wide as your arm span, then the electrons would all be whizzing about inside the volume enclosed by your fingertips. Meanwhile, the nucleus would be sitting in the center, and its diameter would be smaller than the width of a single human hair. So all of the atoms that make up you and me and all the seemingly solid things in the universe are mostly empty space. Now, this is incredible, but what is even more mind-boggling is that empty space is not truly empty. I know because I've seen it. This is a simulation by Professor Derek Leinberger at the University of Maryland. It was made using a supercomputer to crunch the calculations of quantum thermodynamics. Now, that is the theory of fundamental particles called quarks, the building blocks of protons and neutrons, and how they interact with each other through gluons.
What you're looking at here is the energy density of the gluon field fluctuations. Where the red spots come out, the energy density is very high, it fades down color. So in the lowest energy field fluctuations are not rendering this animation, so we can actually see into it.
And what we see is a bubbling soup of quantum field fluctuations that come and go incredibly quickly. The frame rate of this simulation is 1 million billion frames per second. Now that is truly high speed. The dimensions of this box are absolutely tiny. They are millionths of a billionth of a meter, roughly enough space to stick 2 protons. But there are no protons here. This is a simulation of the vacuum on its own, what we normally think of as empty space.
Empty space is actually full of these important gluon field fluctuations. And on average, it is possible to.
Okay, so that's Derek Leinweber, who actually was responsible for these massive supercomputer calculations that are boiled down to the picture. Now, how do we know that that's all correct? It sounds very fanciful. All this stuff talk about what's going on in empty space. How do you know that what's going on in empty space? Well, the point is that these fluctuations in empty space are what determine the behavior of quarks and what prevents them from separating with each other. They are They find it very difficult to move through this oscillating soup of fields that are constantly pointing in different directions. And that's why they have a hard time separating from each other. Each one makes a disturbance in this mess, and they get tied up and can't move away from each other. So that's all hand waving. That's kind of an explanation after the fact of what the calculations show. But the calculations can be checked because in these computer calculations, you don't only simulate the properties of empty space, but you look at what kind, if you inject some energy into empty space, inject, say, 3 quarks and let them settle down into let them settle down into a low energy stable object, a proton, you can measure the energy or the mass of what they've settled into, that is the proton. And by doing calculations of that sort, you can see if our theory, which started with just quarks and gluons, none of which have ever been observed, whether it produces the particles we do observe and nothing else. And here it is. You find that there are many, many particles that were discovered in the course of investigations of particle physics. They have names like pi meson, rho meson, k meson, k star, eta, eta prime, omega phi. And then N is nucleon, that's protons and neutrons. And then it had the neutron, that has a number of relatives that contain strange quarks like the lambda, sigma, and cascade particles, delta, and so forth. There's many, many particles that people discovered in the 1960s and 70s, a zoo of particles that we now understand as being like the energy levels of a single atom in different levels of excitation, or a few different kinds of atoms, a few different, we can compare the calculated masses, which come from a theory where the quarks and gluons have basically zero mass. So all the mass is due to the motion of these fields and the energy involved in those motions. You sort of read Einstein's equation, E equals mc squared backwards to get the mass in a concentrated region where there's lots of energy equal to the energy divided by c squared. That's how the mass of all these particles arises, and the numerical agreement between the calculated masses and the masses actually observed is now perfect and has reached the precision of a few percent. So that's a fantastic result, that a theory that's based on degrees of freedom, none of which you actually observe, as its output gives you the particles you do observe and nothing else. And by the way, this explains the origin of mass in terms of energy. Most of our mass can be traced to the masses of protons and neutrons. There's small additional pieces from electrons, but almost all of it comes from protons and neutrons. And that's what you see here, arising from a theory in which the masses of the objects, the quarks and gluons that are relevant, are essentially zero. So all of our mass, the nucleon mass, is here calculated as being due to pure energy. So this is a case where computation has really solved the main problem that was facing the theory of quantum chromodynamics, namely that its building blocks were never observed, and none of the particles that are observed appear in the original equations. So you have to do heavy computations in order to relate the theoretical concepts to the observed realities. This together, this quantum chromodynamics, the theory of the strong force, together with the theory of electromagnetism, really governs nuclear physics and chemistry, and so the behavior of ordinary matter. And these kinds of calculations was the final and in many ways the most difficult step in completing the fundamental description of matter, and in my opinion is one of the greatest and most amazing scientific success stories ever. And it's based on the application of computation to fundamental physical laws. It would have been completely inconceivable without supercomputers to do these difficult calculations. There are many other calculations waiting to be done with new algorithms and more powerful computers. This is the beginning of the story, which I think will flourish in coming years as people learn to calculate complicated molecules and the behavior of complicated nuclei, and be able to control matter with great precision, thanks to the possibility of doing calculations that solve the equations we can't solve by hand. Now, I'd like to pass briefly from the sublime to the, I wouldn't say ridiculous, but far out stuff. The bottom line of the preceding discussion is that it's possible to write the operating system of the world, the fundamental equations of physics, in a form that computers can understand and use unambiguously to calculate the behavior of matter, which kinds of particles exist, and how they behave. It's not the operating system would be very much slower than the physical world, but in principle, the operating system of the world can be written as a short set of a short computer program that contains all the laws, and the only question is solving them. It would be a much shorter program, for instance, than the program that is the operating system of any modern personal computer, and much, much shorter than the program that operates Word, for instance. So we have a remarkable mapping between the physical world of laws and particles and physical objects and the world of concepts that you can tell a computer, and the computer knows what to do with it to do calculations that map directly on to what we see in the world. And that success makes us wonder whether we can take it further. Could we get even simpler rules that that go into a program? Or could we even imagine that the mapping should go the other way, that there should be a concept world that's the primary reality, and the physical world is really a secondary manifestation of what's going on in a world of concepts? This is the philosophical doctrine of idealism, or mind over matter. So let me briefly show you both of those things, which are entertaining and at least some of it is at the cutting edge of current research. Perhaps the most remarkable and well-studied system where simple rules give rise to very complex behavior is the mathematician John Conway's game of life. Let me very briefly explain what that is. It's a game that's played on a computer with a grid that's just a planar arrangement, like a checkerboard of many, many squares, some of which are active or alive, we say, and some of which are inactive. They don't have anything and don't have a mark in them. And the rule of the game of life is what tells you when you have some configuration of active and inactive squares at one time, what it'll look like at the next step. And then you follow the next step, the next step, the next step, the same rule. And the rules are very simple. They're written down here. If a living cell has fewer than 2 neighbors, it dies. So here's a living cell that has only 1 neighbor, it dies. Dead cells that have 3 neighbors become alive. That's called reproduction. If you have 4 nearby neighbors out of these 9, out of these 4 on the corners, then you die of overpopulation. Otherwise, there's no change. So those are the rules of life. And those rules seem incredibly simple, and yet they can give rise to rich dynamical behavior. This is an example that follows the rules of life called the glider gun. And what it does is a kind of dance where it spits off these little messages to the external world systematically as a function of time. So this gun sets off these things, and this can be used to make a computer out of that. Just using the game of life, you can send messages from one part of your system to another. You can design little systems all from the just following the rules of game of life that do computations. Technically, you can build a Turing machine, and so you can do any calculation that any computer can do. In principle, if you wait long enough, you could get a Conway game of life to do. So it's very appealing to think that the world might be down to a few simple update rules. And you can get interesting models of many things in this way. It's the subject that's called Cellular Automata, and you can read about it on the internet, and there's a vast literature, and you can download programs that you can play with to see the behavior of these things, that can be very rich. And they can be used to model interactions in society and so forth with different rules, with the growth of wildfires, the growth of pandemics, the growth of populations. Just having these kinds of rules will allow you to do that. However, so far, this approach hasn't worked very well as a model of fundamental physics, despite efforts of some very bright people. The reason is that the fundamental physics really uses heavily the idea of continuity of space and time and symmetry of different directions, and these things are just very, very difficult to mimic in cellular automata. Another direction related to this, sort of at least at the level of metaphor, is that computation could be a deeper level of reality with fundamental physics, and somehow the physical world being an illusion or a simulation inside a computer of some kind. This is perhaps most familiar in popular culture as the theme of the Matrix movies, where, well, the actual plot is quite confusing, but it does seem that what's going on is that the characters don't realize it, but many of them, most of humanity is not real, but is being in suspended animation and fed an illusory reality on a computer. However, it seems far-fetched. First, there's the embarrassing question of if the world is running inside a computer. I should say that this idea has been discussed a lot and advocated by people like Elon Musk and Nick Bostrom and other people who should know better. But there's an embarrassing question, which is, if the world is running inside a computer, what's the computer made of? If the world was programmed, what was the programmer made of? And most of all, to me, if any of these ideas are true, why is the program so inefficient? The physical world that we inhabit has, as we saw in the case of protons, a lot of hidden complexity. Now, if you were programming a world, the last thing you'd want to do is make it out of objects that have had a lot of hidden complexity. Hidden complexity is useless. Also, it has a lot of constraints that, from the point of view of programming, seem quite arbitrary. In computer programs and computer games, it's quite possible to move through time backwards, to relive things, to have effects on objects that are very far away. If you've ever played Super Mario, you can see that if you're allowed to violate the laws of physics, you can have a lot of fun behaviors that are very, very easy to program. Why doesn't the world use those obvious possibilities? And all I can say is that it's possible to imagine a simulated world, but if ours is such a world, then the mind that creates it, made of God knows what, works in very mysterious ways. Okay, so let me pass then from these general considerations of how simulation has been a tremendous influence in enabling us to do calculations in physics that we couldn't otherwise do, and to suggest some wild ideas about different formulations of physical laws. But the wild ideas are based in a profound idea that the physical laws we know can be stated in a short computer program. To talk about something a little more down to earth, namely physical approaches to a wide class of useful problems called optimization. And I'll show you how to cast optimization, a very wide class of interesting and important practical problems, in terms of physical processes of cooling and annealing. So first of all, let me show you how you map logic problems onto problems of minimizing energy. This is the key link. So many important problems can be mapped onto the problem of satisfying a large number of logical constraints. So, for instance, you might want to say that either x1 is false or x2 is false, or both. So if you know that well, you can. I invite you to make examples of this kind of thing. I'll keep it abstract in the interest of saving time. Another clause is either x1 is true or x2 is true, but not both. So this symbol means not, this symbol means or. So we have not x1 or not x2 means either x1 is false or x2 is false. And this one is not x1 or x2. So this one says that either x1 is false or x2 is true. But then you also want to have and x1 is true or x2 is false, and so forth. You can make, and you can easily convince yourself that you can make very, very complicated, in fact, arbitrary logical statements by these kinds of formulas. And if you go to a supermarket and look at the Logic Problems magazine, you'll see zillions of problems that are very amusing that can be cast into this form. Or if you're an aspiring lawyer and want to prepare for the LSATs, they have logic games of this kind that logic problems that are stated in words but can be restated in terms of these kind of formulas. So they're recreations, they're also test items, but they can also be, you can also map problems like the traveling salesman problem of finding efficient routes to traverse cities, or problems in scheduling airline flights. Many problems can be mapped onto satisfying a bunch of mathematical constraints of this general kind. I won't go into the details of how you do those mappings, but it can be done, and it's basically straightforward. Now we want to cast this enormous class of problems coming from law or recreation or industrial design or scheduling problems or inventory logistics problems, all those things. We want to map them onto physics problems so that we can use the method of physics to address them powerfully. And here's how you do that. Let's use spins to represent true or false. They don't have to be spins, but spins is a convenient thing to talk about. They could be a high and a low voltage. They could be a lot of other things. But let me just say, we need two values to represent true or false, so we can take spin up and spin down in a certain direction as representing true and false, respectively. And then the strategy is to make the spins interact in such a way that every false statement contributes a positive amount of energy. So for instance, here, it's best explained in an example. Here, this quantity, 1 plus the value of the spin 1 in the z direction, multiplied by 1 plus the value of the spin 2 in the z direction. If either one of them is false, then this will be 0, because one of these will be 1 plus minus 1, which is 0. But if both of them are true, so if you violate our canonical assertion, not x1 and not x2, then this will be a positive quantity, namely 4, because it'll be 1 plus 1 times 1 plus 1. So if we can set up our spins to interact in an appropriate way so that their energy, depending on how they're relatively aligned, is given by this function, then what we've done is impose a penalty for every mistake, an energetic penalty for every mistake. And we did that for the clause I showed you, not x1 or not x2, but you can do a very similar trick, and I invite you to experiment with it. You can do a very similar trick for any of the logical constraints we want to enforce. So you can map all the logical constraints onto interaction energies so that every time you make a mistake in satisfying the constraints, your system has a higher energy. So that means that we set up a situation where our physical system encodes the problem in the sense that the physical system has its lowest energy states are the ones that do the best possible job of satisfying the constraints. Every time you don't satisfy a constraint, it adds to the energy. So the best that you can do is satisfy as many constraints as possible, make the energy as low as possible. So this is a very, very powerful trick. and allows us to map these logical satisfaction problems and by similar tricks, many, many other problems onto the physics problem of finding the low energy states of an interacting set of spins or some other thing that represents two values, true and false. How do we minimize? So that's the physics problem. How do we solve it? Well, one way to drive a system into its low energy states is to make it cold. That's maybe the most straightforward way. And physicists have a lot of, physicists and engineers have a lot of experience in making things cold, and they're quite good at it. Yeah, we take for granted our ability to do that in the ice boxes. But the underlying principles are things that physicists study in and chemists and engineers in thermodynamics classes, the underlying theory of how you make refrigerators work. And you can make more sophisticated versions that use, instead of pumping gases, you pump spins with magnetic fields that are very well adapted to getting energy out of spin systems. So the kind of system that I talked about as embodying the satisfaction problems, and you make them cold. This is a look ahead to next time, and I'll be talking about quantum computers. A key element of quantum computers is making the system very, very cold, and this is the refrigerator that enfolds that the Google quantum computer. And most of what you see here is a fancy refrigerator. The actual computer is a little thing inside. Okay, so you can cool things in refrigerators, and that's very important, and in my opinion, actually underutilized. But you can also implement cooling in software. So we know what the microscopic kind of interactions are that make things cool. And just as we implemented the interactions of QCD on a computer by putting the equations mathematically, in programming equations mathematically, we can do that for a system in contact with a refrigerator too. It's called the heat bath method. And that's a powerful way to using physics to solve interesting, important computational problems. A more sophisticated version of that is called annealing, a problem that often arises when you try to cool an inhomogeneous system. And these spin systems are very inhomogeneous because we put the interactions in such a way that they're dictated not by normal nearest neighbor interactions, but by logical constraints. You can find that there are big domains that are hard to flip, and it only becomes advantageous if all the related spins flip at once. This is the notorious problem of local minimum. So if we have an energy function that might be very complicated, if the energy is here and you have little changes that don't change the value of the relevant parameter very much, you get stuck at this minimum, which is not the true minimum. And there are a number of local minima that you can get trapped at. This is kind of an idealized situation. In real problems, like in chemistry, you get very, very complicated energy landscapes. And if you want to get to the minimum, you have to avoid getting trapped in these false minima. So how do you do that? Well, blacksmiths and metallurgists discovered an effective way to address this issue, which is don't cool too fast, because if you cool too fast, you remove the energy and then you can get stuck. But cool very, very slowly. So or do some strategic heating to allow yourself occasionally to jump out of a local minimum and take a moment, go up in energy for a little while, so as to explore possible ways of getting over barriers into places where there's hidden better possibilities for low energy. This is called annealing. So the annealing process in metallurgy is you take your metal, heat it, allow it to crystallize, and as it cools, restructure in a better, more perfect form. Here's a picture of what's going on at the micro level and what it actually looks like at the macro level in an annealing furnace. And here's the result if you do it nice, slow annealing, so you don't take away energy too fast, you get much clearer, nicer structure with bigger domains that are coherent than if you do it too fast. So this can be done in software, as I said, and there it's called simulated annealing. And it's turned out to be a very powerful technique for solving optimization problems. I'll show you a little video of how effective it is in finding the shortest route for a salesman who wants to visit all these cities exactly once. So you start off with some random, more or less random guess for which city to go, which order of cities to take, and then you cool it down, impose energies, and take the energy out, and it settles down into a very good path. That's an efficient way of visiting all these cities. So you can see how the process of sucking out energy forces the path. You can think of this as a sort of like almost like a string that's getting tauter and tauter because you take the energy out, you pull it tight. Okay, so that's simulated annealing. Let me move on to discuss now reversible computing, the third topic I wanted to talk about. And I'll make this fast because it's getting a little late. So arithmetic and logical operations are generally not reversible. For instance, if you know only that x1 or x2 is true, that doesn't allow you to reconstruct the values of x1 and x2 separately. It might be that x1 is true and x2 is false, or it might be that x1 is false and x2 is true, or it might be that both of them are true. You can't really tell if all you know is that x1 or x2 is true. In other words, if you process the values of x1 and x2 onto the value of x1 or x2, that's an irreversible operation. For many years, people took it for granted that computation must be irreversible, but they were wrong. This was discovered in the 1980s, primarily by a man named Charles Bennett at IBM. Here's the beautiful dirty trick that allows you to do reversible computation. What you have to do is, when you do a computation, make sure that every possible input corresponds to one possible output. So every possible input that you have at the beginning, of your computational step, corresponds to one and only one computational output. I'll show you that concretely in a moment. That's exactly what this OR statement didn't do, because we had several different inputs mapping to the same output. But let's see how we can do OR in a reversible way. So here's OR, and it's not reversible. You have different outputs giving different inputs here, giving the same output. Now I'll show you how to make it reversible. And once I show you this, you'll see how to make anything reversible. Okay, so here's the thing. You start with your x1 and x2 and add another thing, x3. And when x3 is 0, you just have the and you had before. You want to preserve that because you want to have x1, you'd want to be doing the and computation. If that's the goal of your computation, you want to compute and. But if you want to do it in a reversible way, you have to also preserve the information, and this doesn't preserve the information. So what we do is allow we expand our space of inputs so that there's a third input. Only when that third input is 0 do we do and. If the third input is 1 instead, we do other things. And then on the output side, we also want to make sure that we never have two inputs that are the same going into the same output. So how do we fix that here? Well, we add two garbage variables, G1 and G2. We don't have to call them garbage if you want to use something more dignified, but two variables whose only reason to exist is that we want to make our computation reversible. And their role in life is to break ties so that when two inputs here threaten to give the same output, we have additional outputs that break the tie. So here we had three possible inputs that gave the same output. Now we have in this third direction, breaking the tie by having these extra outputs that are always different. And then to do that, we needed to add two additional outputs. So in order to get a mapping so that every single input corresponds to a distinct output, we have to have equal numbers of inputs and outputs. So we need a third input, that's x3. And then we can just more or less arbitrarily fill in the rest of the entries in order to make sure that every possibility appears exactly once on the right-hand side, and every possibility appears exactly once on the left-hand side. So now we have realized and, which originally was not reversible. You couldn't reconstruct the inputs from the output in a context where in this larger framework, you can always reconstruct the inputs from the output. So you could run this computation either way. You don't destroy information by doing computation, is the deep message. This is a reversible thing, and yet it gives us a way of computing or. And if you think about this, maybe a little hard to digest at first, but if you think about it, it really is fundamentally simple. And once you understand it, you realize that you can make any computation reversible using this kind of trick. So today, practical computing is not reversible. We don't want to keep an extra lot of garbage bits. Also, in order to keep things reversible physically, we have to stay in equilibrium. That usually means doing things slowly, and in computing, we don't want to do things slowly. But it's a fundamental point of profound interest, I think, that in principle, computation can be done reversibly. And this inspires the idea that computation can be done without destroying the principles of quantum mechanics. In other words, we can do it in a fully quantum mechanical system, and we'll be exploring that next time. to conclude this one, I just want to go back to the classical problem of Maxwell's demon, which is very much connected to this question of reversibility and information and computation. So Maxwell's demon was an imaginary being that was empowered to violate the second law of thermodynamics. The second law of thermodynamics basically says that heat always flows from a warmer object to a colder object, not the reverse. But if you had a demon that allows energetic atoms through, when you have these two components of a gas on the two sides, and say this one is colder and this one is hotter, the colder one will still contain some energetic atoms, and whenever they come by, the demon opens the trapdoor, lets it through. When a cold atom comes by, it closes the door and doesn't let it through. And in this way, you can transfer energy from the cold object to the hot object. So what's wrong with this? This was a paradox posed in the late 19th century by Maxwell and caused decades of hot debate in the physics literature. What, if anything, is wrong with this demon? Does it point out a profound limitation to the second law of thermodynamics? So, however, we should ask the same question here as we asked in the context. So, we should ask the same question here that we asked in the context of the matrix, or a simulated world. What is this? What is the computer made of? There we asked. Here we should ask, what is the demon made of? If we regard the complete setup of demon and material as a whole, and we ignore the demon's internal state, we would be mapping, that is, in this process where the demon is allowing the hot molecules through but not the cold ones, we would be mapping many states of the original system onto fewer ones. We would be, in technical language, we would be compressing phase space, but thinking about it simply, we would just be taking many possible input states and mapping them onto the same output by systematically separating the hot molecules so that they only appeared on the left. And the basic equations of physics, however, always preserve the number of states, and so they don't allow you to physically realize the operation that the demon is supposedly doing, that is to take many internal states, many states, and map it onto fewer states. The only way that could work is if the demon is actually a complicated object that has many states of its own. So the demon has to have lots of internal states, and in squeezing or taking out possible states from the remaining part of the system, it has to use its own internal states. And as long as the demon is a finite object, all those states get used up. Or to put it in vivid language, the demon gets hot and confused. It can't work forever because it just gets heated up and all its states get fused. Let's relate that to computation. One way to sort things is by computing, and we can sorting things is a primary operation of computation of computers, big subject of computer science. So in this way, we decrease order, or in the jargon of physics, we decrease the entropy of the system that's being sorted. So if that were the whole story, if there were no overhead for it, it would violate the second law of thermodynamics. And that's why people thought that it couldn't be the same story. Computation would necessarily involve entropy generating processes, or in other words, irreversibility. Now we see that there's a different possibility. This analysis of reversible computation shows that no, computation doesn't necessarily generate entropy. It can be done in a reversible way, but only if you keep all these garbage bits. And that goes back to the idea that Maxwell's demon will fill up with useless information and go mad and cease to operate because it will run out of storage space if it tries to do a lot of sorting. But it can still work on a small scale for a while, and we'll see how that unlocks conceptual possibilities for quote unquote, violating the second law of thermodynamics effectively on a small scale for a while and doing very interesting things technologically. So next time we will turn from these conceptual issues of reversibility and the relation of heat and information into concrete technological applications and the state of the art, and how these fundamentals constrain how the state of the art is going to develop and what is possible. So let me summarize. We've covered a lot of ground in this lecture, but they can be summarized in a few major points that should shine through the maybe somewhat bewildering details. One is that large-scale computation has become an essential tool in modern physics. We saw how it enables us to solve the main problem of QCD, for example, the mismatch between the elements, the building blocks of the theory, and what you observe in the world. And it also gives us fun new kinds of models, for instance, cellular automata, that can give us new ways of thinking about complex systems. However, physics discourages the idea that we live in a simulated world. The way the actual physical laws work doesn't look at all like a cellular automata or any simple computer program, or any efficient computer program, I should say, for doing the things that the physical world does, or that we would like to do in order to make the physical world interesting. Then we discussed how cooling and annealing are a powerful approach to computational problems, and the deep basis for this, that you can map a wide variety of computational problems onto the problem of minimizing the energy of physical systems. And that finally, that computation can be done reversibly, but to do that requires major overhead. You have to keep track of a lot of useless information, and you can't do erasing. So those are the main points I wanted to cover today, and thanks for your attention. And next time we'll decrease the level of abstraction and talk about the actual technology of computing. Okay, so we have some questions from last time, and I'd like to very briefly try to address those briefly. Questions that were mailed in. So let me read them. Some of them are very, well, all of them are interesting in one way or another. Thank you for submitting them, and I encourage questions in the future. So first question was from Emmeline. If dark matter does not interact with electromagnetic waves, what does it interact with? Well, it does interact with electromagnetic waves and lots of other things, just very, very weakly quantitatively. That is, theoretically. We have no reason to think that the interaction is rigorously zero. It's just that existing experiments have not been sufficiently sensitive to see what must be a very, very weak interaction. So for instance, specifically in the case of axions, which I mentioned, I think, in the first lecture, but we'll discuss in great depth, in depth in the upcoming colloquium, we have one of the frontiers of doing research on dark matter, and in particular on axions, is exploiting the very, very weak but non-zero predicted interactions of the axions, or dark matter in general, with electromagnetic fields in order to get a signal from the axion interacting with electromagnetic fields of them making disturbances in electromagnetic fields, which those are the kind of things we know how to measure. So that's the whole art of trying to detect axions, is to exploit their very weak but non-zero interaction with electromagnetic fields in order to demonstrate their existence. So it's like when you pick up the signal of radio waves using a radio receiver, the signal can be very, very weak, but if you design the right kind of receiver and tune it to the right station, suddenly you get a good response. And that's what we're hoping to do, that if we have the right kind of receiver and tune it in the right way, we'll pick up the otherwise hidden signals of dark matter that's all around us. So thank you for that question. The next question is from Ishan Hamant. Oh, Hamant Ishan, sorry. Does dark matter exist in every galaxy? Can dark matter emerge from ordinary matter? So those are two questions. I'll try to answer them very briefly because there are quite a few questions and we can go on for a long time. Does dark matter exist in every galaxy? Yes, almost certainly. According to theory, maybe there are very, very rare exceptions, but generically, in fact, it's better to think about it the other way. The galaxies we see are kind of impurities in dark matter. Remember, the dark matter weighs about 6 times as much in the universe as a whole as the ordinary matter. And the theory of formation of galaxies that now appears to be working very well in numerical simulations is that what happens is the dark matter congregates gravitationally and starts falling in, and the ordinary matter follows it. But the ordinary matter is a relatively minor component of the mass, only 1/6. But the ordinary matter finds it easier to lose energy and sort of collapse into more compact objects and compact objects and light up. So that makes the visible galaxies, but the visible galaxies are kind of contaminants inside a bigger structure of dark matter. Today we see as the dark matter halo around the galaxy. The second question here was from Hemant was, can dark matter emerge from ordinary matter? I'm not sure exactly what you mean by emerge, but presumably the question can be, can ordinary matter decay into dark matter? It's conceivable, but that is a kind of interaction, and all interactions are expected to be very, very small. Otherwise, we would see matter disappearing effectively if a lot of matter decayed into dark matter. So in principle, yes, at a very low rate, but in practice, it's very, very rare. Okay, next question. Well, there's a whole series of questions from Barbara. And these questions are at least the first two are very sophisticated questions. Can modified Newtonian dynamics serve as an alternative explanation rather than dark energy? And do galaxies like AGC 114905 present a challenge to dark matter theories? To really properly answer those questions would require a detailed technical discussion, but in my opinion, which is I think is the most common opinion, although not a complete consensus, is that the modified Newtonian dynamics, which involves changing the laws of gravity instead of introducing a new component of matter, is not a viable alternative to the dark matter and dark energy picture. The dark matter, as I showed, I didn't discuss dark energy very much, but I did allude to it. It's clearer in the case of dark matter that there are many, many independent kinds of observations that can be understood in a uniform way by postulating that there's a new kind of particle that makes dark matter that behaves mostly in normal ways. It just happens to interact very, very weakly with ordinary matter and with itself. And that explains many observations. If you change gravity, it's possible to fit one kind of observation, but it's very difficult to fit them all in a consistent way. And also, these theories are just terribly ugly. Yeah, I don't think they're a serious competitor to the dark matter and dark energy hypotheses. And I don't know what you. It's ignorance on my part. I don't know what's going on with the galaxy AGC 114905, but people who study dark matter cosmology, professional astrophysicists, seem to think it's in pretty good shape. Okay, so next question from Barbara is, what makes dark matter dark? What could it be that it isn't detectable by any of our usual methods? Well, I discussed this by example last time. At one time, Neptune was dark matter. At one time, neutrinos were dark matter. At one time, gravitational waves were dark matter. Dark matter is something that we haven't yet developed the technology to detect. And the current cosmological dark matter is something that appears to exert gravity in different places in the universe, and there's a lot of different effects that has, which I discussed, but we haven't detected it by any other method yet. I hope that'll change in the near future, but at the moment, that's the state of things. The next question is from Barbara. Could dark matter be antimatter we haven't happened to have observed? It can't be antimatter. Antimatter is not something that interacts weakly with ordinary matter. In fact, it interacts very, very strongly with ordinary matter. If we were surrounded by antimatter, as we are surrounded by a dark matter halo, if the halo were actually made of antimatter, we'd be in really bad shape because it would be annihilating the ordinary matter, and it would be very obvious. So no, it can't be antimatter we haven't observed. Okay, so next the question is from Stuart Lindsay. Hi, Stuart. Why is the light mass ratio for nearby galaxy work for nearby galaxies, but not the Coma cluster? No, I'm sorry. I may have given the wrong impression because I gave a historical account of the observations. At the time when Zwicky discovered this anomaly between estimated mass to light ratios in the Coma cluster and estimated light to mass ratios in other galaxies that had been studied, it was really comparing very different methods of assessing the amount of mass. In the case of the Coma cluster, you could estimated by calculating how much mass there would have to be to bind the coma cluster together in a stable way. When people estimated mass to light ratios of nearby galaxies, what they did at that time was basically calculate how much mass was in stars that they could see and how much light was emitted by the stars and gas clouds that they could see, and just calculate the ratio of the amount of light to the amount of mass. But they didn't, so it was measured, they were measuring quite a different thing, actually. And what they called the mass was a mass determined just by adding up the masses of the known objects you could see, whereas the gravitational way evidently adds in more things that you don't see. So nowadays, the light to mass ratio that you see, that you measure properly using gravitational measures like rotation curves, they show dark matter also in nearby galaxies. So it's not the case that the coma cluster has different light to mass ratios than normal galaxies. Historically, there was a mismatch, but that now is understood, and the coma cluster has one, so to speak. Okay, then we have Srihan. We know that gravity affects time. An object in space that exerts a strong gravitational field also slows time. Black hole. What does the existence of dark matter mean for gravity and thus time? How does it affect those two phenomena? Well, it has the same effect as other kinds of matter. So any distortion of time that you would get from ordinary matter, you'd also get from dark matter, because dark matter gravitates in the same way as ordinary. It's non-gravitational. Different interactions are unusual, but not as gravitational interactions. Okay, then we have Richard Hazinski. What makes gravity special in that everything interacts with the gravitational field, but most things don't interact with the other fundamental fields? Well, first of all, that's a good question, but let me first correct it a little bit. It's not true that most things don't interact with the other fundamental forces. Most things do interact with the other fundamental forces. Many particles are charged. Even particles that aren't charged, like photons, participate in electromagnetic interactions. Most particles have weak interactions. Quarks and gluons, which are a lot of particles, have basically half the particles have strong interactions. So even neutrinos have weak interactions. So all the particles in the standard model have either strong, weak, or electromagnetic interactions, and most of them have participate in several of those interactions. Nevertheless, it is true that gravitation is more universal than the other forces. And basically, it's because the other forces respond to different kinds of charges, electromagnetic charges in the case of, electric charge, as we know it in the case of electromagnetism, color charges in the case of the strong interaction, and what are called weak charges in the case of the weak interaction. And some particles are charged and other particles are neutral, and so the neutral ones don't participate in those interactions. But in gravity basically corresponds to mass, responds to mass, and more accurately to energy. And just about everything has energy. So that's almost part of what it means to exist, is to have energy. So so gravity is a more universal interaction. Actually, okay, maybe I should leave it at that, but just let me mention that you can imagine forms of matter that would not interact gravitationally. This would be topological matter. But that's an advanced topic which we could discuss separately. I don't want to take time for it here. Okay, and number two, I referred to quantum statistics. claiming that fermionic exclusion counterbalances the gravitational collapse of matter in a white dwarf, explaining its form. So that quantum statistics causes a repulsion, but it seems inaccurate to state that probabilities cause. I'm sorry, I have a little problem reading this document. Seems inaccurate to state that probabilities cause forces. Well, this is really a misunderstanding of language. When you say when, and it's not, it's a good question that may be confusing because the language is not really good. When we talk about quantum statistics, it really is not statistics in the usual sense. There's nothing probabilistic about it. So if it were a probability, it would indeed be strange to be talking about it as a repulsion, but it's not a probability. It's a separate thing that indeed does give a kind of effective repulsion.